everyone, and welcome to Groundwater Talk Live. I am Tom Ballard, the Groundwater Guy, your host for the show. And today we're going to be going back to basics and talking about basic groundwater hydrogeology. So we deal with a lot of people with a lot of different backgrounds, and so I thought covering some basics might be a good way to go. We kind of dive into some really technical stuff sometimes, so really covering some basics might be give people some good background here. So I teach some courses on this, and I do have a class where I teach basic groundwater hydrogeology as part of a bigger course. So I thought I'd pull some of those elements in here today and give you a little bit of basic background on groundwater hydrogeology and just so you can kind of understand some of the concepts. So that's basically what we're going to be covering today. Next week, we're going to dive in and talk about karst, actually, and kind of do some of the same stuff but looking at karst geology because it's a little more complex. And where I'm at here in Tennessee, we got a lot of karst, so it's interesting to talk about. But today, basic groundwater hydrogeology concepts, and you should have some tools to really be able to look at and understand basic groundwater hydrogeology. All right, so before we get going, I always ask everybody to like, comment, share. I answer any comments. You leave comments for me, and I will answer those. And likes and comments and shares all help get the word out and help us beat the algorithm as it is. So we can get the word out to people. We broke 100 subscribers here, which was kind of my goal for the beginning of the year. So I'd like to kind of keep building on that and go from there. So thanks, Erica, for being here. So we do have somebody attending live. So thanks for attending. And so today we're going to get back to the basics, like I said, and it's really important to understand because I tend to dive into a lot of technical detail and make some assumptions about what people have in the way of a background. So we're going to cover some of the basic concepts and so you can maybe understand what I'm talking about sometimes. And a lot of this will be old hat for some of you, but for some it might be instructional. So I'm kind of setting this up a little bit different. We're going to kind of do this as like a PowerPoint presentation, and so you're not going to see my talking head too much as I go through the slides, but you should get the voiceover okay. And so this is kind of a little bit of an experiment with me to do it this way, kind of how I had it set up, and here we go, I think. All right, so what we're going to do is we're going to start with the water cycle is really what it comes down to. And this is about as basic as you can get, but there's a lot of confusion with some people, and the reason I put this up here is the difference between surface water and groundwater. A lot of people don't equate those two, but they're all part of the same continuum. So we get water that evaporates, it falls to the ground, then it circulates, it condenses, goes into the clouds, falls as rain or snow. When you get out in California or mountainous areas, the snowpack becomes very important to getting that surface runoff, but also groundwater recharge. So snowpack is really important, but in most places, the precipitation is going to replenish the surface streams and the groundwater. So it's all part of the same continuum, and it's important to understand that a lot of the laws that you see concerning water rights and that type of thing really kind of date back to the 1800s is when the case law came out, when people were thinking about, underground rivers and that surface water and groundwater were not the same. But we understand now that the same continuum. But when we get into water rights issues and the legal stuff, sometimes it goes back to old concepts, and so they try to adapt the legal framework around the current, adapted to the current concepts, and so it doesn't always work. So sometimes water law can really be strange stuff because it separates surface and groundwater, does not always recognize that they are basically continuum. So, and so that's basically what I'm hoping to point out here is it's all part of the same cycle. Water's recycled. They're not making much new water. Sometimes you'll get water created from volcanoes, but mostly the water you're drinking has been around for a while. You're drinking the same water that the dinosaurs drank. So there you go. It's just recycled. So our next concept, and I alluded to this a little bit, was groundwater recharge. So groundwater basically is recharged, and new groundwater as part of that water cycle comes into the water table through precipitation of some sort. We can do artificial recharge, and this is becoming more popular, especially out west in the western U.S. To do artificial recharge, but mostly it's a natural process from precipitation, runoff. The water soaks into the ground, it works its way down till you get to the zone of saturation where all the pore spaces are filled with water, and that is what's called your water table. So the water will work its way down by gravity, and then go into the ground, and you get that zone of saturation, and that's where your aquifer is going to be. So that's going to be your groundwater recharge. This is very important because when we get out in places like California in the last few years, we've had a drought. We have not been getting a lot of precipitation. That has reduced the amount of groundwater recharge available. So what's happened is that water table has fallen substantially. There's not as much groundwater going into the ground. And so what we're seeing is that water table actually falls, and we're seeing wells that are actually in there that are drying up because we're not getting that recharge. So it's really important, not just locally here, but once you get in that zone of saturation, the water will actually move. And we'll talk a little bit about that too, how the water flows below the ground and some of our measurement tools for that. But the recharge is really, really important to have the groundwater available to us. And out west where they've been having the drought, this has been not been happening a lot. So recently they've gotten a lot of rain and snowfall. That's going to help a lot. But you know, the question out west is, will we go back immediately into a drought this summer and where we have reduced groundwater recharge? And that is not good for groundwater because people are still pumping the same, but the water's not going back into the ground or to recharge that. That is really, really important because when you pump more than is going back into the ground through recharge, then what you're going to do is deplete your groundwater resource, and eventually it's going to dry up. You're going to damage the aquifer, and it's bad. California has passed some laws, for instance, that is supposed to safeguard that. They're taking a long time to come into play and maybe not doing as much. I've had some complaints about that I've done in past shows, but there's the concept of groundwater recharge, very, very important to groundwater. The groundwater recharge and discharge, this is a hard concept for people to grasp. Is water actually flowing upwards to streams? But what water does is it flows from zones of high pressure to low pressure. Generally, we think of gravity coming into play, and that's generally true. Is going to be gravity driven. So water flows downhill, but to water in the ground, downhill can actually be the water appearing to move up because it's moving from high head to low head, high pressure to low pressure. So it'll come into the ground here, and you can see the little drawing here, and it'll flow down through the ground, and it'll actually pop back up and discharge into the streams where you have a gaining stream. Where you have a losing stream, we call it, that stream will actually discharge water into the ground. So you can have a gaining stream or a losing stream. This shows actually a gaining stream where the water's flowing into the stream. So now what happens is it takes a long time for groundwater to percolate through the ground. We will get down below the ground and we'll have our upper aquifer, which is usually going to be an unconfined aquifer. That's open to atmospheric pressure, and you will. That's going to be the shortest period of time. It's going to be days or years. The water's going to circulate through there. And then you start to get down into confined aquifer zones. And the confining bed is generally going to be some kind of impervious material like a clay or a shale in bedrock. And it takes a lot longer for the groundwater to work its way through there. And sometimes through cracks and fissures in the rocks is what it does, or cracks in the clay. And sometimes it's just working its way through. So you can see in that upper confined aquifer here, you can have hundreds of years for that water to circulate down there. It's a long time. And then you get into these deeper confined aquifers, and it can be thousands of years, tens of thousands of years for the water to circulate down there, because it's having to work its way down through multiple confining beds and get down there. Groundwater typically does not move vertically very fast, so it's a very slow process. All right. Now, precipitation comes into play here. This is kind of my area, and I lost kind of some of my chart here, but in the translation when I converted this to a PDF. But this is kind of Tennessee, Kentucky, Illinois, Indiana, Ohio area. So this is just a interesting contrast here, because you can see annual precipitation. This is from 1951 to 1980, so a little out of date at this point, but it's a good illustration that shows we get up in Illinois, and you're talking 36 inches of rain per year. We get down in Tennessee, which is actually a very wet state, and we're getting over 60 inches of rain a year in some places, so almost twice what they're getting in Illinois. So groundwater in Tennessee is fairly plentiful. We have plenty of water down here. A lot of that has to do with our precipitation. And so precipitation is really, really important to the groundwater. That recharge is what keeps our groundwater full. And you see in some states, we got, if we put this map out in California, you'd see it was even less. So in some places, you barely get 10, 12 inches a year, and that's really desert environment. So you're pumping a lot of water out of there. You're taking out more water than is going in, and you got problems. All right, so let's get into types of aquifers, and boy, once again, my slides didn't come out quite right, but it's all readable. So we really have two types of aquifers. We have an alluvial aquifer, which is going to be sand, gravel, clay, silt in layers. That's going to be, those are generally going to be your highest yielding aquifers. If you can get into a nice sand and gravel, that's going to probably be your highest yielding type of aquifer out there. Then we get into fractured rock aquifers. These are going to be bedrock type aquifers. So what we're really looking at there is fractures. Now, I did say that alluvial aquifers tend to yield more. An exception might be karst, and we're going to talk about karst next week in the show. But karst, where it forms caverns and conduits and limestone, you can get some very high yielding wells from karst. But for the most part, the yields in a bedrock aquifer, even if we're finding these fracture zones that have the water in them, they are going to yield less than typically. On average, they're going to yield less than alluvial aquifer. So these are the two types of aquifers we're looking at. Example of an alluvial aquifer might be the Central Valley in California, or you get over west of the Tennessee River in Tennessee. We start to get into the Memphis Sands and those type of alluvial aquifers. That's what I'm talking about. Fractured bedrock aquifers, you get up in granites, and you're going to mainly be dealing with fractures. That's just the way it is, and we're always looking for the fractures to find where the water is in those particular rocks. So keep that in mind. We talked about confined versus unconfined aquifers. Generally, an unconfined aquifer is going to be an aquifer that is not going to have a confining layer over it like a clay. It's going to be open to atmospheric pressure, so the water table is going to fluctuate up and down. and with the recharge and pumping rates and those types of things, you're going to see it fluctuating up and down. A confined aquifer is an aquifer that's down below a clay, so it is tends to not have a water table per se, and the water is generally going to be under some kind of pressure. So if we look off to the right here in our confined aquifer diagram, you got a couple wells here. That upper well, aquifer 1, is an unconfined, and you can see where the water level is. The aquifer 2 is a confined aquifer. The well we have there is actually under pressure. So what will happen is the water level will rise in there, and you can actually get artesian flow in some circumstances. And artesian flow is where the pressure of the water under the ground actually causes the flow out, the free flow out the well. So the pressure head is actually above the ground surface in that case. In this case, we're looking at something less than the ground surface, but it's under enough pressure where the water level will actually rise to above where the unconfined aquifer is. So this is not an atypical situation. You'll get different water levels, and that is, if this was open to the air like that would be where the water table would actually be. So it's kind of a hard concept to grasp. Confined aquifer, it's under pressure, it's stored under there. So when you poke a hole in the confining layer and get into that aquifer, it's actually going to push it up like in a straw. So that's a confined aquifer. All right, let's talk a little bit about properties of aquifers. So this is where we get into the hydrogeology, and yeah, here's a nice picture of an artesian well. That's a free-flowing well. So it's a confined aquifer. The water pressure is the head pressure is enough that it actually pushes that water a few feet above the land surface. So it's actually a free-flowing well. We used to get a lot of these back in the old days, but we've pumped so much groundwater that artesian wells are pretty rare anymore, unfortunately, because they are a beautiful sight. And this is just really a good picture here. But okay, so we're going to talk about some basic concepts of aquifers. We're going to talk about porosity. We're going to talk about effective porosity. We're going to talk about hydraulic conductivity, which is a really important measurement, specific yield, specific retention, transmissivity, and storativity. These are all important properties of aquifers. And an aquifer really is where the water is stored in the ground, whether you're in a sand and gravel aquifer and it's in the pore spaces in between, or whether you're in a fractured rock aquifer and it's in those fractures. That's the porosity. And that's going to be our aquifer. All right, so let's first talk about porosity. What we have here is you have a volume of dry sand, and this is just our illustration here. So you have a cubic meter of dry sand, and there's going to be a certain amount of open space in between those sand grains. That is going to be our porosity. So in this particular case, we have a porosity it's 30%. So we can fit a third of a cubic meter of water in between the sand grains here. So we can dump that water into the sand, and you will then have a saturated sand, just like an aquifer. And that's going to be 30% of that space in that cubic meter is going to be taken up by water that's going to occupy the space in between the sand grains. That is our porosity. So that is the maximum amount of water we can fit in there. In this case, it's going to be 30%. That's going to vary depending on the type of aquifer and the aquifer conditions. Aquifer can change laterally. It can change horizontally, vertically. And so these conditions can change, so it becomes very challenging to just, arm wave and say our aquifer has 30% porosity, because you need to measure that, and we do that through pumping tests and other measurements, and so we'll talk a little bit about that later. But this is the basic concept of porosity. Now, here's some examples of porosity. You got this upper left, you have high porosity, so you have the sand grains, and all that blue in between is water in there. So that's going to be getting you in your 30-35% range porosity. Off to the right there, we have moderate porosity, so you have some smaller sand grains filling in around the bigger sand grains. That's going to reduce the amount of space that's going to be available for the water, so you're going to have a little bit more moderate porosity. There in the middle, we have minimal usable porosity. So you have cemented sand grains, you have a shale, and so you're going to have a small amount of porosity in there. And then we get into fractured bedrock, we're going to have low porosity, and then it can be low to high porosity depending on how broken up that bedrock is and how interconnected the fractures are. So if you just have a fracture that's got water in it, that's not as good as a whole series of interconnected fractures where the groundwater can move to the well and you can recharge that water. So bedrock will vary from low porosity to high porosity, and we'll talk a little bit about the concept of secondary porosity here, because most bedrock in and of itself, unless it's fractured, has low porosity. And to get porosity, you got to break it up, and that's called secondary porosity. We'll talk about that in just a minute. Now, an important concept here is effective porosity, because not all that water that is in between the sand grains in your aquifer is going to be available to be pumped out of the ground. There's going to be a certain amount of water that's going to occupy dead spaces. It's not going to flow. Water will have a natural adherence to the sand grains, so there's always going to, effective porosity is always going to be less than your total porosity, because you're never going to get all the water out of the aquifer. It will not happen. Physics comes into play here. These are physical properties of water. It's going to adhere to the sand grains, and it just can't flow out of there. You're going to see that dead space in there that's occupied by the water. You're not going to get that out, and so effective porosity is always going to be less than your regular porosity. Effective porosity is really what we want to deal with when we're looking at yields on wells, because that's the water we're going to be able to get out. The theoretical porosity doesn't mean anything to us if we can't get that water out of the ground if we're dealing with wells. So effective porosity, and you'll see how we use this in some equations here in a little bit, but effective porosity is really that water that's going to be available to us. Now, here's our secondary versus primary porosity. So primary porosity is the porosity that represents the original pore openings when a rock or sediment is formed. If you have a granite, that's going to be about zero. So if you're in a sandstone, there's going to be some porosity there. If you're in a limestone, it's going to be very low unless you have karst limestone developed. Secondary porosity then is developed in a rock after its deposition as a result of fracturing or solution. It's usually not going to be uniformly distributed. So this is important, and it becomes a lot more challenging to find, to place wells in rocks where we're looking for fractures and development of secondary porosity. So it takes some science to do that. A lot of times in alluvial aquifers, you can move the well 100 feet this direction or that direction and get pretty much the same results. That is not true if you're in a fractured bedrock. It comes down to exactly hitting those fractures. And that's a lot of what I do is tracking down those fractures and getting the best well possible in the circumstances. So here's an example here. Karstic limestone has relatively low primary porosity because limestone just the water does not have a lot of pore space that can flow through. But it can have high secondary porosity due to development of solution cavities and channels. We'll talk more about karst next week, but suffice it to say, you develop these solution cavities, channels, caves. You can flow a lot of water through karst, but it's not flowing through the limestone itself per se. It's flowing through the actual solution cavities and channels, and that's what's important. If you're looking for wells there, it's important to find those, and that's where your water's going to be. So this is just an illustration of that, going back to our you know, alluvial versus bedrock aquifers. So same illustration, but you're just now here we're kind of looking at primary openings versus secondary openings, and you can see in the sand, our primary porosity is developed, around the sand grains. In bedrock, it's in the fractures or to the right there. It's going to be the caverns and the conduits in the limestone. So that's primary versus secondary porosity. You can see in the bedrock off to the right there, the lower right. That granite is just not going to, water's not going to flow through granite because it's all hard formed. There's no pore space in there, so you got to have the fractures to develop in order to get the water. All right, let's talk about the concept of hydraulic conductivity, and that's something that's um, all right. So hydraulic conductivity is an important measurement for hydrogeologists because it is how we measure the flow through the rocks, the ability of the rocks to flow water through them. So this is the formal definition of hydraulic conductivity. It's the volume of water at the existing kinematic viscosity, which is basically the standard viscosity at basically at room temperature and flowing through the rocks. So that's big words, but we're standardizing it. Then we'll move through a porous medium in unit time under unit hydraulic gradient. So that's the slope measured at right angles to the direction of flow. It's generally designated as K in most groundwater equations. So you hear hydrogeologists talking about K a lot, and that is hydraulic conductivity. It's really, really an important measurement that will come into play in a lot of other calculations we do. But really, what we're doing is we're looking at the flow along the direction of flow. And that's going and I got a picture here. I'll show you what this looks like, but it's and here it is here. So you have, for instance, confined aquifer. You take a little slice out of that aquifer, and what you're doing is you're measuring here. You can see on the right here we have Q, which is actually the flow through there. We have the gradient, which is the difference between the water level on one side versus the other side, and so we're using those parameters to actually define the flow through that little section of rock there. Then we can translate that to the entire aquifer and really come up with a decent approximation of how that water is flowing through the aquifer and the rates. And we'll use that in basically some other equations here that I will show you. So here's some examples. You can see you range all over the place. We get into the bedrock, the igneous and metamorphic rocks at the top. Big difference between unfractured and fractured, really low hydraulic conductivity in unfractured rocks, higher in fractured rocks. You look on the bottom here, and gravel and clean sand is generally going to give you your highest hydraulic conductivities. There in the middle, you have carbonate rocks, which are limestones. You're going to go from fractured to cavernous, so big difference in hydraulic conductivity there. And shale, not much unless you get fractured. The same way with sandstone. So it's gonna vary a little bit all over the place. So you can just see the general ranges for hydraulic conductivity. Generally, you're going to get the best aquifers developed in a clean sand and gravel alluvial aquifer, that like I was mentioning earlier. But you can do pretty well in fractured rock and as well in a cavernous limestone that's got a lot of karst developed. You can get wells that are the equivalent to a really good alluvial well. So it really depends on your environment, and when you get into bedrock, that secondary porosity is everything. All right, specific yield versus specific retention. this gets back to our effective porosity. So the specific yield, that's the part of the water you can actually get out of the aquifer. And that's that part that I showed you when we talked about effective porosity that we can actually, that's not occupying dead zones or adhering to the sand grains. That's the water that will actually flow out under the influence of gravity and come into your well for extraction. Specific retention is then just the flip side of that. That's the water that is retained as a film on rock surfaces or in very small openings, that dead space. That is your specific retention. So effective porosity plays a big part in that. This is kind of, going back, looking at that illustration. So we go back and say, okay, we have our 1 cubic meter of saturated sand. We might have an effective porosity of 0.2 cubic meters here, or 20%. So we're going to be able to get 20% out, or basically 2/3 of the water that was in the rock. You're going to retain 1/3, and that's going to be adhering to the sand grains or in the fractures in the rock. You can see the illustrations on the right. So in this case, your porosity is 30%, but your specific retention is going to be 10%. Your specific yield is going to be 20%. So we're never going to be able to get that 10% out that's going to be your specific retention. So that's the water that's going to be available to you to pump out of the ground is going to be that 20%. Here's just some, interesting specific yield, specific retention of different rock types. You can see peat, which really isn't a rock, really has both high specific yield, high specific retention, but we get down to gravel at the bottom, and you can see the specific yield is actually pretty good. Specific retention pretty low. We get into sandstone. Sandstones will yield pretty good because they have some porosity. Now, the interesting thing is about clay. Clay will hold a lot of water. There's a lot of water in clay, but you can see that the specific retention is very high. Clay does not have a very good effective porosity. So the amount of water you can get out of clay is very, very low. You'll get some out, but for the most part, it has a high specific retention because the effective porosity is really low. There's no interconnected spaces for that water to flow out. So even though pretty high, you can get 40% of clay can be saturated, you just can't get that water out. And we can see the rest here, how it varies. So just kind of interesting facts there. Head is, we break it out into total head. We have elevation head and we have pressure head. So elevation head is really the bottom of the well above a datum, which is usually going to be sea level. The pressure head is going to be the amount of water that's in the well itself. So from the bottom of the well to whatever the static water level is, that's going to be your pressure head. So we break it out, but as a practical matter, head, and you'll hear head referred to, that's basically just the pressure where the water rises to in the well. It's just the elevation above sea level of the standing water level in the well, or as we call it, the static water level. This is an important measurement to us, especially when we do pumping tests, because we're going to look at the static water level versus our pumping water level. That's going to be drawdown, and so this is going to give us some idea of our aquifer properties. All right, this is what it looks like when we calculate our groundwater flow, because for here we have a unconfined aquifer, and we see the gray area is our groundwater, so the dashed line is our water table. We're going to see a certain slope there. The water is flowing. In an aquifer, the water flows in some direction. We want to measure that flow direction, but we want to also measure the gradient. There's a difference. The groundwater flow direction and the gradient are different. The groundwater velocity is something. How fast it flows is another measurement we can make. But the easiest way to measure the gradient is basically just to calculate the difference between two wells, usually along parallel to the direction of groundwater flow, and that'll give us our actual gradient. So it's usually going to be foot per foot is how we're going to measure that. So we're looking at the water level in well one, the water level in well two. The difference between the two is our head loss. That's going to be our delta H, and so that's going to be our gradient as long as we're along that flow direction. And then the distance between the two wells is going to be L, and so we're going to be using that in our calculation for both gradient and groundwater flow direction. To calculate actually the gradient, we're going to need three wells actually. So if you look off to the left here, we have well one, we have well three, we have well two, and the head in well one is 26.26. The head in well 3, 2607, and the head in well 2 is somewhere in between. It's going to be 26.2. So really what we want to calculate, we want to draw a line between, this is a simple 3-point problem in hydrogeology. So we want to draw a line from the highest to the lowest, and then we want to see where on that line the elevation for the static water level or the head for well 2 plots, and that then we'll plot that and we'll draw a line from well 2 to that point on that line, and that'll be a straight line. And then our groundwater flow direction is actually going to be perpendicular to that line. So that's how we calculate the flow direction. So now we've calculated our actual gradient. We've calculated our flow direction. So those are some basic units of groundwater measurement. We know what the slope of the groundwater surface is and which direction it's going. This could be important in contaminant studies, for instance, is where's that groundwater flowing? Is it flowing towards our well or away from our well if we have contaminants, and is that a point of concern? Groundwater gradient is something we calculate all the time. Okay, so principles of groundwater flow. These are some basic equations we use in groundwater flow, and one of the first ones is Darcy's law. That's Henri Darcy was a Frenchman. He did a lot of initial calculations on groundwater flow, and we still use his law today. It really takes two forms here. So, and I lost my formulas here, so I apologize for that, but really groundwater flow, the formula really isn't important here. I guess the conversion lost these formulas here, but what we want to know to come up with our groundwater flow rate is the flow rate, the volume of flow, the hydraulic conductivity. We're going back to that hydraulic conductivity, the head difference, and the distance between the points. So that's our groundwater gradient. So that's really going to give us our groundwater flow. So if we want to look at the volume, now we're looking at how much water is flowing out. So that's Q, that's what we're calculating here. So what we do is we multiply the aquifer cross-section area by the hydraulic conductivity times the head difference divided by the distance between the points to give us our gradient, and that'll actually give us the flow through there. The rate is actually the flow, and that's hydraulic conductivity times the head difference divided by the distance between the 2 points. So I apologize for that. I didn't notice my formulas were missing here, but that's your basics there. So we're calculating. We can use Darcy's law to calculate both our flow rate and the flow volume through the aquifer. And my goodness, I lost it here. We can actually calculate the velocity here too. So I apologize. This is not good here. I lost my formulas, but what we can do here is we can use our Darcy's law and make some other changes to it to calculate actually how fast the groundwater is flowing. And this is going to be important in contaminant studies as well. So this is going to be the average linear or seepage velocity, you'll hear it called. So we're going to take into account the effective porosity, the flux or the discharge, or the amount of water flowing through there, the cross-sectional area of the aquifer, the hydraulic conductivity, once again, the groundwater gradient, which is going to be dH divided by dL, and that then is going to give us our average velocity, linear velocity. Now, this is going to be an approximation because you're flowing in and around sand grains, and so it's not going to be actually a linear flow, because if you dive in at a microscopic level, you're actually taking a more circuitous route. But this gives us a linear approximation, which is relatively easy to do, to tell us how long our groundwater or how fast our groundwater is flowing. This one actually worked out. Transmissivity, this is the capacity of an aquifer transmit water at the prevailing kinematic velocity. So once again, our hydraulic conductivity comes into play. Transmissivity is really looking at the aquifer in total. So what you're doing is you're taking to get transmissivity, and that's going to be the amount of water that's flowing through the aquifer, the entire aquifer. It's going to be your hydraulic conductivity. Once again, the importance of our hydraulic conductivity number, just multiplied by the thickness of the aquifer. That's going to give us an idea of that cross-sectional flow through the entire aquifer. Very important number for determining how much water is going to flow through your well. The last of our calculations really is storativity. That's how much water can be stored in the ground. So, and the water that will be released when we pump the water. So it's going to be different in an unconfined versus confined aquifer, because in a confined aquifer, the water is under pressure. So it's compressed somewhat. It's hard to compress water, but it's compressed somewhat. So you're really getting water from decompression of the water in the aquifer in a confined aquifer. So we calculate storativity a little bit different for an unconfined aquifer versus an aquifer. I'm not going to go through the calculations on that because they're a little more complex, but what I did want to talk about here is relative storage capacity versus depth. So this is especially true in bedrock storage capacity. So we generally, you're not going to vary too much in alluvial aquifer. It's going to be, you're going to have as much water, generally deeper, because they're generally going to be relatively shallow. But you start getting down into bedrock and you're dealing with fractures, you get lithostatic pressure. So the pressure of all that rock up above is going to take the deeper fracture zones and it's going to start to squeeze them shut because of the weight of all the rock overweighing them. So those openings are going to be less frequent with depth unless you have some really significant faulting and breakage going on. So as a general rule, we look at here in Tennessee, about 400 feet is about as deep as you're going to get those fractures. Now, when we're looking at karst, generally karst is 200 feet or less. And maybe you get some paleo karst, but that's, we'll talk about that next week. But but generally 400 feet or less in a fractured bedrock is generally a good rule of thumb. You can go deeper if you're looking for bigger faults and you've mapped those out, but generally that's going to be the rule of thumb if we're just looking at fractured bedrock. And off to the right here, you got a little illustration showing your relative capacity with depth. So the alluvium pretty well retains its capacity for the entire depth, and then you start to lose storage capacity as you go deeper in the fractured bedrock. All right. Oh, here's our storativity calculation. So I think what's important here is that when we look at storativity, it's going to range. So in our storativity calculations, it's going to range from 0.01 to 0.3 in an unconfined aquifer. In a confined aquifer, storativity is going to range from 0.001 to 0.00001. So really low storativity, but once again, remember, you're taking that water that's compressed and decompressing it, and that's where the water is coming from. Now, sometimes we start to pump these confined aquifers, and you actually dewater the aquifer. This is bad because what happens is now you start collapsing down the storage capacity of that aquifer. It's supported by in a confined aquifer, the water storage is supported by an intricate network of drains that are kind of fit together there, and you start dewatering these confined aquifers where they're not saturated anymore. You start to collapse that structure down. You never get that back. So you can pump water down there all you want, but if you've collapsed that structure and you get the subsidence that collapses that structure, now you've lost that storage capacity forever. So it's pretty dangerous actually to dewater a confined aquifer. You just don't want to do that. And unfortunately, that's what's going on in a lot of California. And so we're seeing that loss of storage capacity that you'll never get back. So that's just kind of an aside here on storativity. All right, one of our last principles here of groundwater principles is cone of depression. Now, cone of depression, if you're in an unconfined aquifer, you're actually going to be able to measure this because the cone of depression is, as you pump the well, it's going to draw down the water inside the well, and you're going to create a cone that basically slopes to the well, the pumping well itself. So you're going to actually be able to, if you put some observation wells out there, you'd actually be able to measure this directly. But we can calculate that generally speaking. But it's always good to have some observation wells so you can calculate that. And what will happen is we're removing water from the well faster than it can flow in. Water is flowing into the well under gravity. The pump does not vacuum it out. The pump will lift it out of the well itself, but you're not creating this vacuum cleaner effect that some people think a well does. You're basically removing water from the well faster than it can flow in. So you're creating this cone of depression. The water is flowing to the well under gravity, and as that cone of depression increases, as we pull more water out of the well faster than it can flow in, you're going to build a hole in the aquifer and it's going to be flowing in there. We can measure that, and it's going to have a certain velocity that comes in. That's going to affect our well design. But a cone of depression, if it expands out far enough, we can create interference with neighboring wells, and we got to be able to get a handle on that. Now, in a confined aquifer, due to the storativity differences, the cone of depression is actually projected. We can't actually measure it because everything in a confined aquifer is saturated. It's under pressure, so we have a theoretical cone of depression we can calculate, and so that becomes kind of a hard concept to grasp. And I've explained that to people, and they have a hard time getting it. But just understand this is kind of a theoretical cone of depression, what it would look like if we actually had an unconfined aquifer. But we're still creating a kind of sort of, for calculation purposes, cone of depression. All right, so how do we measure these aquifer properties? And that's going to be our pumping tests, is really what we're looking at. So we're going to do, there's several types of pumping tests. We're going to usually do some preliminary pumping to prep the well for the test. Then we're going to do what we call some step tests. And we're actually going to pump the well at increasing rates, no break in between, and we're going to kind of see where our optimal rate is, and then we're going to go to a pumping test where we're going to let that recover and back to our static water level that we've measured ahead of time. And then we're going to do a constant rate test, and that's going to be at our optimal rate that we've calculated from the step test. And we're going to pump that down till we basically get a period of steady state conditions where the drawdown stabilizes for the pumping rate we have. So basically you got a flat line on your drawdown. And then we measure that for a period of time. For instance, in California, we want to have, depending on the length of your test, a 2 to 4 hour period where you have steady state conditions. And usually 4 hours is what we're looking for on that to show that everything is steady state, that we've reached kind of that we're showing that this drawdown is stable at this pumping rate. And then what we'll do is we'll shut off the pump, and then we'll go to a recovery test, which tells us how quickly our water recovers in that well from our maximum pumping rate, or maximum allowed stable pumping rate, I guess you would say. Um, that's an important part, because some states really require this you to pass, get that to recover back to within 2 feet or 95% of your starting static water level within the same period of time you did your constant rate test, or you have a failed test all the way around. So that is an important component. We can actually measure the aquifer properties while we're pumping, both during the constant rate and during the recovery test. We can measure aquifer properties during the step tests. You have a little bit shorter window there, but I'll show you what that looks like. So our goal really with a pumping test is to determine the rate at which a well will balance drawdown with discharge to achieve the highest sustainable pumping rate. Then sustainable means you have that drawdown is not going to change. So you're going to have a drawdown that's not going to dry up your well. So you can go with a higher rate, but you're going to pump your well dry. So we don't want to do that. We want to achieve steady state conditions where we know where the how far we're going to draw that water down in the well. We're going to place our pump intake below that so we don't dry that up, and that's the purpose of a pumping test. Other purposes of the pumping test, we can develop a lot of our aquifer properties from directly measuring our pumping test parameters. Hydraulic conductivity is one, transmissivity, storativity are some of the big ones we can actually directly calculate from pumping tests. And also we'll use pumping tests when we've done a rehab on a well, we've cleaned it up to see what our capacity is after we've cleaned it up, and reestablish that for purposes of going forward. So a lot of different goals for pumping tests, but our main one after we build a well is determine what is our maximum sustainable pumping rate. The way we determine this is we're kind of matching up. We're looking at QA, which is our aquifer yield, and QF, which is our well intake capacity. So you want to plot those up. Aquifer yield is going to go down as you pump with drawdown actually, and over time. So we got two axes here. We have drawdown and we have the pumping rate. So we're really looking for the optimal pumping rate and the optimal drawdown, and that's going to be where the aquifer yield, the well intake capacity intersect, and that's going to give us our optimal pumping rate, which is going to give us our optimal drawdown. So that's really what we're looking at on a pumping test, and then we can pump at that rate, and we know we're not going to dry up the well. All right, so what we're testing, geology is important. Alluvial versus bedrocks have different responses. So we need to know when we're going in what type of aquifer we're doing, what we're measuring, and design our test accordingly. Other hydrogeological parameters, we'll actually measure water quality during the pumping test to see what we're getting in the aquifer. We can actually measure other wells in the area to see how we might affect them if our drawdown cone impacts them. It's important to understand the weather and season can affect pumping rates. You want to probably do your pumping test during the driest period of the year, so that's going to be your worst conditions, and that so that you can really measure the capacity of the well under the most stress, and you know you're going to be safe under pretty much all conditions then. So you want to make sure you understand what your goals are when you set up the test, and that you're really measuring the hydrogeological properties of the aquifer. So we have some software we can use that calculates all this. You can calculate it by hand too, but these days we have software that'll calculate it for you and does a great job. So this is really what a pumping test sets up it looks like for a 1,000-gallon-a-minute well, for instance, you got the pump there, driven by a generator, and we got our flow to waste, and so this is a temporary pumping setup to do the pumping test. This is for a smaller well, domestic well or small capacity well. This is, I think, the 8 or 10-inch well there. This is basically what it looks like there. So not quite as sophisticated. We're using a submersible pump as opposed to a turbine pump, and a little bit less sophisticated, but same principles apply. You're going to see certain things happen during the aquifer. You're going to have your storage in the well bore initially. That's the water that's in the well. Then you're going to have your skid effects that we're going to see, and that's going to be pumping the water out of the gravel pack and right around immediately surrounding the well. If you're in a fractured bedrock aquifer, that's not going to apply. Then we're going to start seeing aquifer response due to transmissivity and storage, where you're actually measuring the aquifer properties. And if we pump long enough and that drawdown cone extends, you may get into boundary conditions. You may get into the limits of the aquifer. So we'll start to see things tapering off, and we can tell we hit some boundary conditions. And that's important to note too, because that may affect our pumping rates as well, because we don't want to get into boundary conditions as we pump long enough that's going to affect our yield. So we may back off a little bit so we don't extend that cone of depression out far enough to get into those boundary conditions. All right, so these are the things we can measure during a pumping test: hydraulic conductivity, storativity, transmissivity, drawdown, spelled wrong. Sorry about that. Radius of influence, specific capacity, which is discharge divided by drawdown, and well efficiency. You got to have a observation well to measure well efficiency. And just to recap, 3 to 4 pumping step tests is generally what we'll do for the step test to dial in our rate. Then we'll go to that constant rate test, and then the recovery test that we talked about earlier. This is kind of our setup. We're going to have a test well with the pump, and we're going to measure. We need to measure our drawdown. We need to measure our pumping rate. Those are the two parameters that are important to measure. So we're going to measure our water levels, usually with a hand water level meter or a transducer. I tend to use both just as a backup system, because pumping tests are expensive to do and you don't want to redo them. If you just use a transducer and it fails on you, I mean, I get paranoid enough. Sometimes I'll do 2 transducers and still do manual measurements. So because you spend $30,000 on a pumping test, you don't want to have to redo it because your equipment failed. So redundancy. You want to record when the pump goes on and off, and any oddities that go on, just to make notes so it helps you interpret your results. This is what a step drawdown test looks like. This is in our Octasolve pumping test analysis software, and you can see our different pumping tests, the little curves there, and we can see that on the bottom one it kind of flattens out there. The ones up above, the one up above starts to flatten out a little bit, and then the ones up above don't really flatten out. So kind of our optimal pumping rate is somewhere in between the bottom 2 ones that we're looking at. Generally with a step test, you're going to start with your lowest rate and start cranking it up, and then we're looking at what our rates are there. All right, constant rate test. Generally 8 to 24 hours. If you're in a bedrock condition, that's generally going to be either a 72-hour or even a 10-day test, because it's a little bit tougher to assess fractured bedrock. You're going to end up wind up with boundary conditions more often. So we really want to make sure that we're extending that test on a bedrock aquifer to make sure we actually test the actual conditions we're going to encounter during actual pumping conditions. So once again, you're going to do drawdown till you hit steady state conditions, and you're going to do the recovery test. Data collection, elapsed time, depth of water, drawdown, pumping rate, other parameters such as electrical conductivity, pH, and temperature. Sometimes we'll measure those. We'll also tend to grab our water quality sample during, if it's a new well, during the ending stages of the pumping test, because we know we're getting a representative sample from the aquifer. And we're also going to want to take any notes of the pump on and off and that type of thing, is, anything unusual that's going on to help us interpret our results. That actually comes in handy from time to time, that you get some weird results, and you happen to put some notes down that help you um, figure that out. So, all right. So this is an example of an actual pumping test we did on a winery well in California. There was two wells there. There was an old well. There was a new well we put in. The driller put the new well in the wrong location. They were actually looking for about 50 gallons a minute well, and so what we're looking at is here. The red is actually drawdown at the old well, so we're actually using that as a monitoring well. The blue up above is the drawdown at the new well, and then the green is actually the pumping rate at the new well. So we can see here our sustained pumping rate at a drawdown of about 300, somewhere between 300 and 325 feet. We got stable drawdown. Our actual pumping rate was about 22 gallons a minute, which is far less than what they were hoping and expecting. Bottom line is, we looked at it and said, you put the well in the wrong place, and we were not involved in siting the well, so they just put the well in the wrong place. But this is actually shows you how you interpret the data, and this gives us the data we need to know. They needed to put another well out there. They needed to put it in the right place, and unfortunately, they just kind of went with some wrong recommendations on this. All right, so that's the end of the show today. Kind of long, talking about hydrogeological principles and pumping tests, but you kind of get the idea, and hopefully that gave you a good rundown. It was kind of quick, but still an hour. And next week we'll talk about karst. So thank you for listening. If you want to be a guest on Groundwater Talk Live, this is the link to become a guest, and we'd love to have you on. If you can, if you got some good information on groundwater or water systems, we'd love to have you on as a guest. We stream into the Groundwater Guy channel on YouTube, and all our past shows are there. Also into LinkedIn Live when it works. It looks like it's working today. Has not worked the last few weeks. LinkedIn can really be flaky, so I always try to stream to LinkedIn. Sometimes it just doesn't work. So, but all our shows are at the Groundwater Guy channel on YouTube, so you can see the past shows there, and we got quite a few up there at this point. So a lot of useful information there. Check it out. Thanks for watching. Don't forget to subscribe to the Groundwater Guy YouTube channel, and we will see you next week.